On this video, we will talk about Cavaliers' principle. So let's get started. Let's start by looking at the small introduction question which states, let's take in consideration the solid on the right hand side and let's think about how will we find the volume of this solid. Well, the first thing that we notice is that this it's definitely not a right solid because if you take a look, there is some kind of a curvature. So this is not a right solid. So perhaps we cannot use the formulas that we have discussed in the past. What I mean by formulas are the ones that we have discussed in the past. So there must be a different way for us to still find the volume of this solid. Well, how about if we take a look at the base of the solid, which seems to be a triangle, and we find the area of the solid, or the area of this triangle. And once we have found the area of the triangle, how about if we go exactly a little bit on top of it, and we see that it's also another triangle here. And how about we find the area of that other triangle? By adding those two areas, notice that I'm definitely finding some height in this curvature solid. And how about once we have find the area of the second triangle, I go a little bit on top of it and I find the area of this other triangle. Now notice that by doing this, by finding a lot of areas is by adding them up. All I'm doing is I'm finding the volume of this figure. So perhaps one strategy that we can use is we find numerous areas, perhaps in terms of base, right now my base was a triangle, and we add them up. And again, just to, when we add, numerous areas, what we're doing is we are finding the height of the solid. So what would be another way that we can perhaps think of that we can use that strategy to define the volume of the solid? Well, another strategy could have been, how about if I just cut this figure into a lot of triangles and then I just stack them vertically. So forget about the curvature in a second. Let's say we just cut the solid into a lot of triangles here. And then once we have all those triangles, how about we just stack them vertically? In other words, how about if we cut a lot of triangles and then we just stack them all vertically? Now these are all the different triangles that we are discussing here. So perhaps another strategy that we can use here is that we can rearrange the figure. And then find the volume. And then we can say we can find the volume of, I'm going to call it new, in quotation marks, figure or solid. That's another strategy that perhaps we could have used of. And there's different ways that we can think about how we can definitely find the volume of a solid that perhaps is curved. But what is exactly Cavalier's principle? Cavalier's principle is going to help us answer this question. How can we find the volume of solids that perhaps are curved or slanted? And before we start defining Cavalier's principle, let's take a look at the following animation here, or illustration. And once we see the illustration, we're going to try to answer these three questions. So let's go to this illustration. So here we have our illustration, which notice that it does have this curvature solid that we were referring to in our introduction question. And what we're trying to do is we're going to try to answer this question. So what are some similarity between both solids? And this is what I mean by both solids here. But the first similarity that I can think of is notice that at least the base of this solid that is curved here, it is definitely a triangle. And notice that this second solid here, it does have a base of a triangle as well. So perhaps we can start saying that both solids have bases of triangles. And perhaps we can go a little bit further. Perhaps we can say that, well, perhaps they have the same base area. But we don't know this yet. But, I mean, it seems to be the same triangle as a base on the left figure as you do have on the right figure. So perhaps they do have the same base area. But we'll see that in a second. Now, the second question is, well, what are some differences that both solids have? Well, there's a huge difference, at least the way that the solids are being defined. Notice that the figure on the left-hand side, it does have some kind of a curvature on it, where the figure on the right-hand side, it definitely seems to be a solid who's a right solid. Because notice that at least the heights are definitely straight, where on the left-hand side, we do have some kind of a curvature. So that's a huge difference between those two solids. So what we can write here as a difference, well, first, they look different. One looks like a right solid, and the other looks slanted. I'm going to call it curve. The other one looks curved or slanted. But now, will there be any relationship between the volumes of the two solids? Well, let's see. Well, at least on the solid on the right hand side, we can definitely see that we can use some of those formulas that we do have, that we have discussed in the past. We can definitely find the area of the base and just multiply by the height, and we can definitely find the volume of the solid. But at least a figure that is slanted or curved on the left hand side doesn't seem to be that straightforward. But what if I tell you that they have the same volume? The volume on the figure on the right hand side, it is equivalent to the volume on the figure on the left hand side. And why is that? Well, there's two ways that we can think of. The first one is, how about if we start cutting the figure on the left hand side in a horizontal way? So let's transfer some of the slabs here. So notice that if I cut the figure with some height on it, notice that that is equivalent to the same triangle that we do have on the right hand side. And if I cut the second one here, notice that if I stack on top of it, we do have the same figure. And if we keep doing this, I'm just going to press play. And if we keep doing this, notice that this is the first strategy that we were discussing on our introduction. What if we start cutting this curve figure and then just restack them in a different way? And notice that I'm just going to let it run. Notice that we keep doing this, the whole figure seems to have the same height. So even though the figure on the left hand side was curved, notice that if we cut by a certain height and we keep stacking them, they have the same solids. They have the same volume. So therefore, the volume on the curved figure, it is equivalent to the volume on the right figure. At least with our animation here, they seem to have the same volume, so they need to have the same volume. So this is one way that perhaps we can see this, and this is what we refer to as Cavaliers' principle. And we're going to talk about the requirements in a second. But another strategy that we also discussed was, well, I know that if I transfer them out, which is what I'm just doing here, both figures are going to have the same solids. Instead of transfer them out just like it's going on here, how about if we don't do that and we just rearrange the original solid? How about if we just notice that we're still talking about the same triangles. Notice that we, instead of curving it, notice that this is completely slanted. And again, even if it's completely slanted and we use the same idea, this, and I'm going to fast forward here, we're still going to have the same solid as the figure that we do have on the right hand side. So how about we just redefine the figure that we were given initially? So here we have what was initially given to us. And it doesn't really matter how we curve this figure, those solids, those two solids are still going to have the same volume. So how about we just rearrange it in such a way that now it's completely identical. And this is a little bit more, we can definitely see more clearly that those two solids have the same volume. And this is what we refer to as Cavalier's principle. Regardless of if a figure is right or perhaps a little bit slanted, or even if it's curvature, if, if both figures have the same base area on the bottom and the top, and they do have the same height, both figures are going to have the same volume. And that's what we refer to as Cavalier's principle. That's just one of the applications of Cavalier's principle. And now that we have discussed this, how about we go back to our discussion, our lesson here, and it's completely answer this question, which states, is there any relationship? Well, we already saw they have the same volume, and we're going to say this, that this is because of Cavalier's principle. And now for illustration number 2, it is still the same illustration, but just with the second method that we were discussing. What can we state about the volume of both figures that are shown in the illustration? We have already discussed this, and we have already said that both figures have the same volume. They have the same volume. So now that we have discussed and kind of visualized what Cavalier's principle is stating, let's actually apply it in some quick problems now. Well, let's take a look at example 1. Notice that what we want to do here is we have a solid, which is not a right solid, but the cylinder is actually a little bit slanted. Can we still find the volume of this slanted cylinder? Well, we definitely can, because now we can think of our illustration, and perhaps this cylinder, perhaps we can think of this cylinder as being a cylinder who, instead of being slanted, it is straight. Because notice that we're still having the same idea. Here we have a circle. Here we have a circle. And all we're doing here, we're just stacking up circles, one on top of the other. Here we would stack another circle. And notice that all the circles have the same radius. So regardless of how we stack our circles, we're still going to have the same volume. Notice that here, what we're doing, we're just stacking the circles in a little bit of a slanted way, where if we were to think of this as a right cylinder, we still have the same circle here. And now we're stacking another circle on top of it. And if we continue stacking the same circles, notice that all we're going to do is just going to have the same volume, because we're essentially talking about the same figure, so nothing has changed here. So now to find the volume of this slanted cylinder, it will be equivalent to just finding the volume of this right cylinder, where notice that we're still talking about a height of 3 meters, And now notice that here my diameter is of 2 meters, so perhaps my radius is of 1. So regardless, if we think about a slanted or right, we're still gonna have the same volume. So if we know that we can think about it as equivalent to each other, then I'm just gonna find the volume of this right cylinder, where remember that the formula for the volume of the right cylinder is pi r squared times the height, where this is pi, what the radius is 1, times the height, where the height is 3. So this is equivalent to just 3 pi meters cubed. And we know that we have the same volume due to Cavalier's principle. And the same can be said about the example on the right hand side. Now, does the stacks of coins have the same volume? Well, it's almost the same idea here. Regardless, if we would have a right cylinder, if I take a look at my circles here, or in this case our coins, if I find the volume of this right cylinder, it will still be the same volume as this other slanted or curved cylinder, as long as they have the same height. And as long as we do have the same base. Because notice that we start talking about here, like we're not changing the coins. So regardless of how I rearrange those coins, I'm still gonna have the same volume. So in this case, yes, they will have the same volume. And we can say that this is due to Cavalier's principle. So our next example here, it's an extension of Cavalier's principle. So let's take in consideration both pairs of solids, and let's find the volume of each figure, and let's try to notice the relationship between the volumes of those pairs of solids. And we're going to try to explain why is it that they have that relationship. So let's take a look at example or pair number 1. And let's find the solid of this figure on the left hand side. So notice that here, to find the volume of this figure, let's take a look at the base, where the base seems to be a rectangle. So we have a rectangular base, and we can see that the height is 20. So perhaps the volume of this figure will be length times width times height, which is equivalent to 480 inches cubed. Now let's take a look at the figure on the right hand side now. So here we have at least our base seems to be a triangle, and it doesn't matter if it's slanted or not. Due to Cavalier's principle, what it's telling me is that I can find the area of the base, and I can still multiply by the height, because notice that I'm still stacking the same amount of triangles here. So to find the volume, I can find the area of the base, which is 1/2 times base times height, and I can multiply by the height of the overall solid to properly find the volume of the all for the overall solid. So therefore, my volume is 1/2 times base, which the base seems to be 6, times the height, which the height of this triangle seems to be 8. So notice that this will give me the area of the base, and I need to multiply by the height of the solid, which is 20. And notice that if I multiply all this, it's still going to be giving me 880 inches cubed. So notice that the figure on the left hand side and the figure or the other figure, we're still going to have the same base or the same volume. Well, let's take a look if we do have that same relationship here on the pairs on the right hand side. To find the volume, let me find the area of the base. Let me use a different color. You have an area of the base here. So here we have a base. Notice that it's a trapezoid. So in order for me to find the area of the base, that's going to be 1/2 times base 1 times base 2 times the height. So this is definitely going to give me the area of the trapezoid. And if I multiply by the height of the whole figure, then I can definitely find the volume. So let's do that. So we're going to have 1/2. The base of my trapezoid seems to be, base 1 seems to be 6. Base 2 seems to be 12. And if I multiply by the height, which in this case seems to be 4, and if I multiply by the height of the solid, which seems to be 10, and if I compute all this, it's going to give me a volume of 360 centimeters cubed. Now let's say we have the same conclusion on the for the volume of the figure on the right hand side. But notice that my base is, in this case, a square. So to find the area of the base, that's definitely 6 times 6. So this is going to give me the area of the base. And if I multiply by the height of the solid, which is 10, that's going to give me still 360 centimeters cubed. So what do you notice? We still have the same volume. But we're talking about completely different figures here, because here my base, it's square, and here my base is a triangle. So how come this figure and this figure have the same volume? Well, if we pay a closer look into the area of the base, if we take a closer look at the area of the base, notice that we're going to have the same value. 6 times 4 is 24, and 8 times 6 times 1/2 is 24. So here we're saying that our area of the base is 24. And since we have the same base and we have the same height, because notice that they both have the height of 20, we're definitely going to have the same volume, because notice that if you measure this, it's going to give you 24 and 24 regardless. And you're stacking 20 of them and 20 of them here. I mean, I'm using 20 because that's the height. So this area gives you 24, and I'm going to stack 20 of them. Well, that's the same thing that I'm doing here. I'm going to have an area of 24, and I'm stacking still 20 of them. And that's one way of seeing as to why is it that we have the same volume here and the same idea here. Notice that if I find the area of the base, and if I find the area of the base, 6 plus 12 times 4 times 1/2, that's still going to be 36. So notice that this area is going to give me 36. This area is going to give me 36. And this 36, I'm stacking 10 of them to get the actual solid here. And that's going to give me 360. And that's the same thing that I'm doing here. Notice that my area is still 36, and I'm stacking 10 of them. So now that's one way of seeing as to why is it that they have the same volume. And this is an extension of Cavalier's principle. Another extension of Cavalier's principle is saying, look, if you have two solids and they have the same area on their bases and they have the same height, they will have the same volume. Same idea here. Notice that my area of the base is 36 and my height is 10. Well, that's the same thing that I'm doing to the solid. My area is 36 and my height is 10. So therefore, we're going to have the same volume. And this has been a small lesson on Cavalier's principle.